Let us continue our discussion on divide and conquer. And in this particular video, we are going to see another sorting algorithm which comes under divide and conquer, and that is quicksort. Now, before we venture into quicksort, let us have a quick overview about the history behind this fastest sorting algorithm. The Quicksort algorithm was developed in 1960 by Charles A.R. Hoare, commonly known as Tony Hoare, while he was in the Soviet Union. He is a guy who won the 1980 ACM Turing Award. He is a British computer scientist and studied statistics as a graduate student and made major contributions to the development of computer languages. One of the quotes of Hoare is, I conclude that there are two ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies, and the other way is to make it so complicated that there are no obvious deficiencies. While studying at Moscow State University, Tony Hoare received an offer of employment from National Physics Laboratory to work on a new project for machine translation from Russian to English. However, because dictionaries were stored on magnetic tape those days, he would have needed to sort the words of sentence into alphabetical order before translation. So, in order to carry out this, Hoare thought of two methods. He came out with two ideas to actually solve this particular problem. The first idea was he would have taken an amount of time proportional to the square of the length of the sentence. And the second idea would actually later manifested as what we call today quicksort. Now, unfortunately, right, at that time only one programming language was available, that is Mercury autocode, and Hoare was not able to successfully code quicksort using Mercury autocode. In 1961, what Hoare did was he attended an Algol 60 class and in Brighton, which allowed for recursion. That means Algol 60 supported recursion. Now, during this course, Hoare programmed an ultra-fast sorting algorithm now known as Quicksort. His first paper on Quicksort was also published in 1961. Now, having known a little bit history about Quicksort, let us plunge into how it actually works. Now, you know it is basically an application of divide and conquer. It's also called as partition exchange sort. Now, how does this quicksort algorithm works? It divides the entire list into three main parts, right? The first one is actually called as the pivot element, which I have written in the second point. Then you have elements less than the pivot element, and you also have elements which are greater than the pivot element. So basically what happens, we choose an element from the original unsorted array as a pivot element. In most of the cases, we choose the first element as a pivot element, even though there is no standard literature written anywhere that you should always pick up the pivot element, right? You can pick up, as a matter of fact, any element, right? And that can act as a pivot element. So let us say for our discussion, we pick up a first element as a pivot element, and then at the end of the first partition, this is how it looks like, right? So you have a pivot element in the between, right? And at the end of the first step, or at the end of the first pass of the quicksort algorithm, the pivot element comes and sits in its appropriate position in such a way that all the elements which are less than pivot comes on the left hand side, and all the elements which are greater than pivot comes on the right hand side. So we call this as a left subarray, we call this as a right subarray. Now we implement the same algorithm on the left subarray, and this is what we get. Now this is the pivot element of the left subarray, right? In such a way that less than pivot are towards its left, greater than pivot are towards its right, and this pivot element, what you see in the middle, this is actually this pivot element, and this greater than pivot is what is this greater than pivot. And the same thing you are going to implement, right, for the right subarray. Now, how does this quicksort algorithm actually works? So first and the foremost thing is you select the pivot element, And after selecting the pivot element, you partition the original unsorted array into two sub arrays, right? And implementation of quicksort algorithm ensures that any whatever the pivot element you have selected in the first point will be appropriately placed. And once you partition, which results into left and right subarray, you implement the same procedure to both left and right subarray to ensure at the end of the day you have all the elements of your original unsorted array in a sorted fashion. Correct? Now, once you choose the element as a pivot element, what you do is you compare this pivot element, right, with remaining n minus 1 elements to ensure that the pivot element is in its appropriate position, right? Now to carry out this, I am going to make use of two variables called as I and j, where my variable I points to the second element. That means it points to the second element of your original unsorted array. And similarly, my j will point to the last element. Now have a look at this, right? So I'm going to make use of two variables, low and high, right? Low is 0 and high is 5 because I have totally 6 elements all the way running from subscript 0 to 5. And I have initial values of three variables. Pivot will be my first element, a of low, that is a of 0. In this case, it is 45. I will be low plus 1, that is 1, and j will be high, that is 5. So with this, I have I pointing to the second element of my array and j pointing to the last element of my array. Now once I have this, the two things that I'm going to do is the pivot is actually compared with the element starting from a of I until an element whose value is greater than pivot element. At this point, we stop incrementing I. Okay, we'll come back to this point afterwards with an example. But what are we going to do with j? The variable j will move from right to left by comparing the pivot with a of j until an element whose value is less than pivot. At this point, we stop decrementing the j. And once we stop incrementing I and decrementing j, we check for the condition. If I is less than j, we swap a of I and j and continue with the same process. If it is false, we swap a of j and pivot and we return the j. Let us have a quick glance at the algorithm. I'm not going to explain you this algorithm as of now. We will understand it with the example straight away. Step number 2, I'm going to call for partition and just have a look at it. Step number 3 and 4 is the where you perform recursion, right? So quicksort is also considered to be one of the good example of recursion. My partition algorithm looks like this. Now let us try to understand this algorithm with the example. So I take same set of 6 elements. I have pivot as 45, I have I as 1, and I have j as 5. So in the first step, I'm going to check whether pivot is greater than a of I. So 45 with 36. 45 greater than 36, it is true. So I increment I by 1 and my I becomes 2. Now when I becomes 2, this is how it is. My a of 2 is 15, so I compare pivot with a of I, that is a of 2. So 45 greater than 15, it is true. So I increment the value of I by 1 and now my I actually becomes 3. So this is how I get it. I is now pointing to 3 where the element is 92. So I'm going to compare the pivot with this 92. 45 greater than 92 is false. And once when this condition becomes false, I'm going to stop incrementing I. Now what's the value of I here? It is 3. So we will get back this value of I3 at a later stage. But now let us shift our focus to variable j. Where is variable j? Variable j is at 5. That is a of 5 is 71. So what we do with this variable j is we now compare the pivot with a of j, right? That means we are going to compare 45 with 71. And what happens? 45 is less than 71. The condition is true, right? Now please understand, when we were discussing with respect to variable I, right, our relational operator was actually greater than. But now, with respect to variable j, my relational operator is less than. So, 45 less than 71, the condition is true, and hence I decrement the value of variable j by 1 and j becomes now 4. Now I'm going to compare 45 with 35 because j is pointing to 4 and a of 4 is nothing but 35. So 45 less than 35 is false. So I stop decrementing j. Understand? Right? So what I have done, I have stopped incrementing I have stopped decrementing j. And once I stop this, right, I'm going to check for the condition. And what is the condition? If I is less than j, right? So I is 3, j is 4, 3 is less than 4, and hence what I'll do is I'm going to swap a of 3 with a of 4, right? A of 3 with a of 4. Originally my a of 3 was 92, my a of 4 was 35, and hence my new set of elements becomes like this. See here, 35 and 92 are swapped. Even though 35 and 92 are swapped, please do not do anything with variable I and j, right? I is still 3, j is still 4, right? So don't touch that as of now. Now we proceed further, right? And what we do is we again shift our focus to variable I. I is 3, right? That's the reason I told we have to continue shifting our focus. Don't reset the value of variable I and j, right? You will land up in no man's area. So 45 greater than 35 is true. So we increment I and now I becomes 4, right? J was already 4. Now see, for the first time in this example, both your variables I and j are pointing at the same subscript called as 4, right? Now 45 with 92. Now don't worry, right? Even if I and j points to the same subscript, that is a part and parcel of this algorithm. You don't need to get panic as a programmer. So I now compare 45 with 92 and I draw conclusion that 45 greater than 92 is false. So I stop incrementing I and then I will proceed with j. I compare 45 with 92. 45 less than 92 is true and I decrement j by 1 and now my j becomes 3. Now watch out carefully. Now my j becomes 3. For the first time here I and j have crossed each other. Value of I is 4, value of j is 3. Now I'll compare 45 with 35. 45 less than 35 is false. I stop decrementing j. Now here the value of j is 3 and I is 4. Now I go back to my if control structure and I'm going to check the condition I less than j, right? Now 4 less than 3 is false because the value of I is now 4, unlike previous case where the value of I was 3. So 4 less than 3 is false. So what I do is I swap a of j with pivot, that is I swap 35 with 45. And then this is how I get my elements. Now watch out. Once you land up swapping the pivot element, okay, understand, once you land up swapping the pivot element, it indicates that that is the that is the end of the first pass of the quicksort algorithm. And see there, the original pivot element 45 is in its appropriate position, wherein the elements left of 45 are less than 45 and the elements right of 45 are greater than 45, right? So it gives birth to two subarrays, the left subarray which will now consist of 35, 36 and 15 and the right subarray which will consist of 92 and 71, right? So your left subarray are nothing but the elements from low to j minus 1 and your right subarray are nothing but elements from j plus 1 to high. Now you implement the same procedure and ensure that at the end of the day the elements are in ascending order. That means what? For the left subarray you can choose 35 as a pivot element and for the right subarray you can choose 92 as a pivot element. Now, having understood the quicksort with the algorithm, let us proceed with the analysis of quicksort, right? Now, when we look at the analysis, what actually comes in mind is the three time complexities: the best time complexity, the average time complexity, and the worst time complexity. Let us have a quick glance about these three complexities. The best complexity in case of quicksort occurs when the pivot element is present exactly at the center, dividing the array into two equal parts, right? And since you know the recurrence relation of divide and conquer, the recurrence relation for this algorithm can be written like this, right? Where this n is nothing but the time required to partition the n elements. Now, having known the recurrence relation for the quicksort, right, let us see the time complexity of this quicksort, right? Now, that is what is given to you already, the general recurrence for divide and conquer, the general recurrence for quicksort. As a matter of fact, let me tell you that the best time complexity of quicksort is exactly similar to that of merge sort, right? By applying the master's theorem, we draw conclusion that the second relation a equal to b to the power of d holds good, right? And hence the time complexity is given by theta of n log of n to the base 2, right? So this particular time complexity, which is there in front of you on the screen in red color, is actually the time complexity of quicksort under best circumstances. Not having going into the depth of how average time complexity is calculated, the average time complexity is same as that of best time complexity. But let us focus a little bit about when worst situation occurs in quicksort. Worst complexity. The worst case occurs when the picked pivot element is always an extreme smallest or largest element. Now that's the problem, right? Now what it says is, or when this actually happens, this happens when the input array, that's your original unsorted array, is already sorted or reverse sorted, right? So if you give input to your program which is already in sorted fashion, and in that sorted fashion or reverse sorted fashion, if you pick up the first or the last element, right, as a pivot element, then the worst complexity occurs in case of quicksort. The recurrence relation for worst complexity is like this, right? Where T of 0 indicates no elements towards left and it can be equated to 0, right? Otherwise, the other two things remains the same, right? Now, let us consider this recurrence relation. Just go through it because it is just a substitution of stuffs in the formula or equations. So I have replacing n by n minus 1 and I proceed replacing n minus 1 by 2 and I keep on going and I get a general formula that t is equal to n of n plus 1 by 2, right? So if function is n of n plus 1 by 2, then I draw conclusion that n of n plus 1 by 2 is actually less than or equal to n square, which is of the form f of n less than or equal to c into g of n, right? You would have seen this form f of n less than or equal to c into g of n in asymptotic notation. And it is clear from this particular relation, my value of c, n0 and g of n. And hence by definition, f of n is O of g of n, and I draw conclusion that the worst time complexity of quicksort is O of n square. Now briefly, we are almost at the end of the quicksort. Correct? Having known all these things, let us see what are the advantages and disadvantages of quicksort. The first and the foremost thing is it is an in-place algorithm since it uses only a small auxiliary stack. It requires only n log of n time to sort n items. The third advantage is it is an extremely short inner loop. And the fourth advantage is this particular algorithm has been subjected to thorough mathematical analysis, a very precise statement which can be made about performance issues, right? One of the prime reason why Quicksort is considered to be the fastest algorithm in the field of design and analysis of algorithms, or actually in the field of computer science. Now moving to the disadvantages part of Quicksort, right? The first disadvantage is it is recursive in nature, correct? Especially if recursion is not available, the implementation is extremely complicated. Understand, right? So that's the reason I was telling you at the beginning that one of the best example of recursion is Quicksort. Another thing is it requires quadratic time, that is n square time in the worst case, which we have already seen. And the last disadvantage is it is fragile. Means what? A simple mistake in the implementation will get unnoticed and it is going to cause the program perform so badly that you will, you basically draw conclusion that as to why did I actually touch upon, quicksort. So a simple mistake a programmer cannot afford to do it. And let me tell you, in real life applications, we don't implement quicksort for a very small set of values, 5 or 6. It's only for the academic discussion, but in real life definitely the input data is going to be tremendously more. Now there is something called as randomized quicksort. Right now, suppose you have some enemy with you. You have an enemy who doesn't like you. Any day, enemies doesn't like us actually, right? And he gives you an array to sort with quicksort, and he knows that you always choose the rightmost element in each sub array. Correct. So how will you foil your enemy? How will you get rid of his problem statement and say that, hey, any amount of problem statement you give, I will be in a position to solve. So you could not necessarily choose the rightmost element in each subarray, right? I would rather give you a suggestion that you could randomly choose an element in the subarray. And unless and otherwise your enemy knows how you choose random location, right, you'll always win. So one of the good thinking according to me is you take three random elements, you have a fair chance of 68.75% if you choose a median of three random elements. Similarly, if you choose a median of five random elements, you pick up any five elements, find out its median, you have 79.3% chances of winning. Similarly, if you go for 11 random elements, you have 93.1% chances of winning actually, right? So this is how you can always get rid of your enemy. You can spoil the foil of your enemy, right? Now, of course, it does not necessarily pay to choose a large number of elements at random and take their median, for the time spent doing so could counteract the benefit of getting good splits almost all the time, right? So it just you have to take a chance. Now, let us conclude about this particular algorithm. Quicksort turns out to be the fastest sorting algorithm in practice. It has a time complexity of n log of n on the average. However, in the very rare worst case, quicksort is as slow as bubble sort. There are sorting algorithms with a time complexity of O of n log n even in the worst case. For example, merge sort, which we have already seen, and heap sort we are going to see in the future design techniques that we are going to discuss. But on the average, these algorithms are by a constant factor slower than quicksort. That is why quicksort is considered to be the fastest algorithm. It is possible to obtain a worst case complexity of O of n log n with a variant of quicksort by choosing the median as a comparison element, right? So that is actually the conclusion of quicksort. But let me tell you something beyond your syllabus as of now, that is only for your information, right? Now, uh, Quicksort has actually gained widespread adoption, appearing, for example, in Unix as the default library sort subroutine. If you are familiar with Unix operating system, if you have worked on Unix, right, there is a subroutine called as Qsort, right? This Quicksort has lent its name to the C standard library subroutine Qsort in Unix operating system, and it is also in the reference implementation of Java. There was a guy by name Robert Sedgwick, right, whose PhD thesis in 1975 is considered to be a milestone in the study of quicksort, where he resolved many open problems related to the analysis of various pivot selections. He worked extensively on quicksort and defended his thesis, PhD thesis in 1975. Robert is actually an American computer science professor at Princeton University and a former member of the board of directors of Adobe Systems. Robert Sedgwick completed his PhD under the supervision of Donald Knuth at Stanford University. Last but not the least, what I would like to tell you is in 2009, there was this guy by name Vladimir Yaroslavsky, Vladimir, okay, Vladimir, who proposed the new dual pivot quicksort implementation. In the Java core library mailing lists, he initiated a discussion claiming his new algorithm to be superior to the runtime library sorting method. Vladimir's quicksort has been chosen as the new default sorting algorithm in Oracle's Java 7 runtime library after extensive empirical performance tests.